Good morning, everyone. Thank you, Dana, for the introduction. My name is Francesco Di Maio. I'm working at Delft University of Technology, and I'm very glad to be here to introduce you the innovative waste-to-plastic technology, innovation technology. I'm going to do this together with Jaap van der Hoek, who is the CEO of the company which is exploiting the technology on the market. We are something like similar like Mr. Rolls and Mr. Royce. At least we would like to be as successful as them. We are really confident that waste-to-plastic solution can turn plastic waste into value, and in doing this, it can benefit the society, the environment, and it will also create a very interesting business opportunities. And in so doing, it will also prevent such a disaster from happening, the one as shown in this slide. Why do I say this? Because in Europe, every year, about 100 billion euro of plastics is used. And of this 100 billion, only 98 billion comes from 98 million comes from virgin plastics, and only 2 billion comes from recycling. Then this should already make you ring the bell that there is a big potential there. And we think that we don't have data for the US, but I think that this data will be even more extreme in the US. In Europe, every year, about 25 million tons of waste of plastic waste reach the end of the life. And of this 25 million tons, only 3 million tons enter the recycling facilities. Because of the inefficiency in the current recycling facilities, only 1.5 million tons are recycled. If the waste-to-plastic solution would be used instead of the current technology, we would double this amount. And then we would reach 3 million tons of plastic recycled, and we would double also the turnover from 2 billion to 4 billion euro turnover. And if waste-to-plastic would also be able to tap into the big amount of the plastic which currently not enter the recycling facility, we could even reach 33 billion euro per year. And then, of course, we would prevent this plastics from creating disaster, because when the plastic is not properly recycled, it can also be illegally dumped in the land, in the river, and eventually it reaches the sea. And we are, as you see, I mean, in the slides, there is a lot of waste in the ocean, and we should do something about that. Because we are going, which world we are going to leave to a future generation. Considering the plastic takes age to be recycled, we should really do something very soon. But plastics has also important environmental impact, not only when it reaches the end of the life, but also at the very beginning, during the production. If you consider that to produce 1 kilogram of plastics, you need about 2 kilograms of oil, and it is a very conservative data. And considering that 280 million tons of plastics is produced worldwide, and 3.8 billion tons of oil is produced worldwide, plastics account for 15% of the whole oil production, and everybody knows that the oil industry is not the most environmental friendly. The key to solve this problem is to valorize the plastics. We should make plastic waste to become valuable. In this way, people will have the incentive not to waste, not to improperly dispose it, and then we will make business, but at the same time we will prevent the ecological disaster from happening. And this is the solution that we propose. Okay, then this is just to prove that we have a pilot plant which has already very big capacity, but later we will come back on that. But what will the benefit to the recycling industry, the waste-to-plastic solution will provide? Now, the point is that at the moment, the plastic waste is, the main source of the plastic waste is in the household waste, the one which people normally trash it unsorted, and the plastics contained in the separate collected one. Now, the current technology, which is based mainly on NIR, near-infrared sensors technology, can only separate plastics contained in the separate collected bins. While the waste to plastic, and another method to separate the plastics, actually, notice I can show you an animation. It does, and the NIR need big pieces of materials to be separated. There is a sensor for instance, for polypropylene, there is a sensor for polyethylene, for instance. There is also for PVC, for PET. And it is separated, but you need the big pieces of the object to be separated. And another method currently used is the sink float, but sink float can be done in water or in alcohol or a mixture with salt, but it cannot be a continuous process. It must be a batch process, and you cannot separate more than 2 materials each time. The advantage of you put materials in water or in salt or in alcohol, and you separate them. The advantage of the waste-to-plastic solution is that it is based on the newly developed technology, which is named the magnetic density separation. The principle of this technology is shown in this slide and in this picture. You can see on the left side a container with some plastics ball which are sinking on water. There is water there. Maybe it's not easy to see, but they are sinking on water. And the container is placed on a big magnet. And you see the plastics are heavier than water and they are sinking. But on the right side, you see that when you place magnetic fluid instead of water, because of the combined effect of the magnetic field and of the mag fluid, which is an environmental friendly solution of water plus iron oxide, you see that there is a gradient of density. Actually, what happened is that the liquid starts to have a different density at a different position from the magnet, so that the plastics you see in red are heavier than the plastics in yellow, and they are floating at, the yellow particles are floating at a longer distance, a higher distance from the magnet, because the density of the fluid in that position is exactly the same as the density of the plastic in that position. And then if you imagine this in a channel, by placing a splitter at a different position, then you can extract the materials based on density. This is what happened in this animation. Actually, it's not an animation, it's a movie, a real movie. The water has been replaced, now it's been replaced by mag fluid, which is this very dark liquid. And then you see that the plastics ball, which in water were all sinking, now they are floating at a different position because the mag fluid get more dense, has a different density at a different position of the magnet. The magnet does not affect the plastics, of course, but affected the fluid. It changes the density of the fluid. Far from the magnet, the density is similar to the water. Closer to the magnet, the density is much higher than the water. Then the particles are floating there. And this is a scheme of the magnetic density separation pilot plant I showed before during the movie. Then you can imagine that by placing splitters at a different position, you can extract different materials in only one go. This is a picture which shows the input is we use shredded materials on the left side, and then it is classified according, it's sorted according to density, and the density difference is very high, accuracy is very high, it's about 10 kilograms per cubic meter. And this is the pilot plant with, which currently has a capacity of 0.4 ton per hour, and it is scalable to 1.5 ton per hour. And now I give the floor to Jaap, who will introduce you with the further development of this solution.
Thank you, Francesco. Good morning, everyone. What you see here is the total solution that we are about to offer to the market. I have to correct myself, this is not our solution, this is the solution that is there today, which is not a total solution. In red on the left, you see the residues, the sorting residues from the current state-of-the-art technologies that are trying to do the best they can on separation of these type of packaging waste plastics. And in red is everything with a negative value, so a waste. And on the right, in blue, you see the positive valued fractions that come out of this system. It has a total recovery of about 39%, so a small 40% of the materials entering the plant are recycled into valuable products. Well, this is then our solution. So where the technology that Francesco just explained is the core of our system, but we are aware that we need to also provide the pre and eventually potential some post sorting to enable the separator to function properly. But in the end, we will have a recovery of valuable polymers of 77%, which is about a factor of 2 higher. Well, our motto is think big but act small, and with that I mean, of course there is a huge potential in terms of the amount of polymers consumed every day worldwide. I'm sorry again for being from Europe and focused on European figures, but I think Europe is about 20% of the total consumption, so a factor of 5 on the 100 billion is what you should expect for the worldwide polymer consumption, with only about 2% recovered from recycling. But we have to keep our feet on the ground, and where are we now today? There we are. What we have done is we have done product quality tests from our pilot installation. We have done the assessment of the processing cost due to the pilot installation. We have a pretty good feeling on what are the losses of the ferrofluid, etc., and the energy consumption. And we have some positive feedback from the market in the Netherlands, which is our local, it's our homeland, so that's where we have the best knowledge on how it fits in the total supply chain. Our short-term focus is on getting our first process line up and running. And to give you an idea of the development curve, in the last quarter of this year we will be producing larger samples for potential off-takers to further validate the business case. And then in the first quarter of next year we expect to complete the engineering of the industrial installation, and we hope to close the deals with the operational partners. And then in the second quarter of next year, the construction of the industrial installation will be started with an annual capacity of about 30,000 tons per year. And then towards the end of 2015, we hope to be up and running. In the next 5 years, we expect to form joint ventures with local recycling companies in the US and in Europe, team up with end users. That's very important, because they are in the end the consumers of our recycled polymers, and we will plan further R&D to further upgrade the product quality. So in the next 5 years we hope to build and operate 1 million tons of recycling capacity and to produce high-grade recycled polymers. This would require about 30 process lines based on the MDS principle and a total investment of about $130 million. In this way, we would avoid about 2 to 3 million tons of oil consumption per year. And to give you a feel, this is about the size of, or this equals the consumption of a country like the UK for 1 week. And this would bring a turnover in direct sales from our process of about $500 million. It will create quite some jobs, up to 2,000. And it will be the natural driving force for the collection of packaging waste instead of dumping it or using it for an energy source, which is of course a lower grade application. And then in the 5 years after that, we expect to further expand our capacity to 3 million tons, and then we think we are more ripe to start working together with the bigger multinational waste and treatment companies. And in the end, what is our ultimate goal is to improve the product quality even more, and to enable the recycling of packaging waste into new packaging materials, products. Here you see a lot of factors that will help our case. Because of the time, I won't go into them. And you may ask who we are. Maybe that's something that I can further explain while answering questions.
Hey, Jan, great stuff. So, any questions? While they're lining up, I've got a question for you. So, if in making these polymers, the energy cost is approximately of oil, so it's 2 kilos of oil for each kilo of plastic, right? What's the energy cost for the recovered plastic here, incomparable?
I'm sorry not to have the exact figure on the top of my head, but it's really only a fraction. The technology that we have is a mechanical separation. So it is some pumps and some shaking feeders and a permanent magnet. Okay. So you can imagine that the cost of electricity are quite low compared to the production from virgin.
We've got some questions.
So tying a little bit to what you were saying, I was curious about how well your process, or how much sort of unique separation and preparation of the materials is necessary to go into your process versus what recycling plants are already using. So the materials coming from the sources, however they gather it, the current processing and separation methods they use for their current recycling processes, how well does your process sort of slot on to the end of that, or is there going to be additional materials preparation and separation processes needed to get into your separation system?
I can go back to a slide. Well, I won't do it. Well, of course, there are some different setups, process setups available in the world. Most of them are a collection of conventional technologies like hand picking or wind sifting, so blowing certain light fractions out of a flow, or magnet separation to remove some potential contaminant metals that are ending up in the waste. We also need some of these pre-processing steps. Our system is a separator and not a washer. So our input to our key technology is shredded plastic waste. So it has gone through a cutting and washing step before. So these processes are available. So we could tap in on such a process line and make it longer and further upgrade the output of those washing lines. But there are also some there's some competitiveness in it For instance, if you look at the sensor-based sorters, which is, Francesco showed, it's the NIR system, the near-infrared sensors. They function on larger items. We can go down to 0.5 millimeter, so that's quite small flakes. But because these sensor sorters are used and operated on entire objects, so for instance a complete bottle, the problem there is that a bottle has it might be produced from PET, but it has a polypropylene cap and for instance a PE foil around it. And this bottle would then end up at a PET fraction, and afterwards it will be flaked and washed, and that will be the end product. But it will be PET with some PP and some PE contaminations in it. Then you can do a sink float afterwards, but then still you have a PE and a PP contaminated remaining flow. And what we do is, because we shred it at the beginning, you cannot use these sensors afterwards because the particles are too small, but the liberation grade of all the different elements on one item is much higher, or almost 100%, meaning that well, we are then able to separate it in all the different items and all the different polymer types. So there is some unmatching overlap, but on the other hand there are also many situations where, well, it fits nicely on existing installations.
Thank you.
Great. We've got a question over here.
Another question on the economics. Considering the pre-processing to get the flakes to go into your process, what do you expect the cost of your raw material to be, and at what price do you expect to sell your product?
Well, for instance, I think in all the regions in the world, the economics in terms of input and output prices may differ a bit. For instance, we know of a case in Eastern Europe where a mixed polypropylene and polyethylene fraction is separated out, which could be a perfect input for this technology. Where the input price for us would be $200 and the sales price would be towards $600 per ton.
We've got a question coming up. I've got another question. In the plastic, coloring agents and coating agents, what happens to those during the process?
Well, in principle, there is no, it's not a high temperature process or no chemicals involved. So it's a purely mechanical separation on very little differences in density. So, well, colors, if in the end, if an item has red polypropylene and also green polypropylene, then the red and the green will end up in the same fraction.
So we'll get brown plastic.
We'll get brown, yeah, this is an example where you would get a brown plastic. And this is also something that I hope everybody realizes, that what we offer here is a special step in the total chain. But there are so many challenges ahead, yeah, to get to a really 100% circular economy. And maybe we'll never get there, but at least we should hope and keep that as a long-term goal.
Super.
But for instance, we are working now on new technology to separate these small flakes into different colors, so that, for instance, in the end, the Coca-Cola red will be able to supply that to a company like Coca-Cola to make new red products.
Perfect. They'd like that. Yeah. One last question real quick. We have about 1 minute.
This looks like a fairly energy-intensive process. Do you have any plans to integrate renewable power generation into the system? And if not, what would be the net gain for what you're saving in petroleum versus what you're having to put into the system to make it work?
Yeah, well, I explained earlier on a question that at the moment I do not have the exact power consumption on the top of my head for this process, but actually it's fairly low energy intensive. We of course, you can always hook it into to a renewable energy kind of form of electricity, which would be which could be beneficial, but it's not the main focus of our project.
Right. Thank you. University of Delft and Francesco, thank you. Great job.
Thank you.